This is just a short video to show you some of the things I've discovered about the body current when using a contact device. This is the SFM circuit board. As you can see, it's fairly simple. The breadboard next to it is a simulator circuit which represents the load that a human body or other biological organism presents to the circuit when it's in operation. I have determined that the body represents roughly a 1500 ohm resistive load in parallel with an 80 nanofarad capacitor. This has implications for the actual current flowing through the circuit. Here we're using a 1 kilohertz square wave with an amplitude of about 15 volts, which is presented to the resistive component of 1500 ohms of the body load. In this case, the oscilloscope is calibrated in milliamperes, not volts. In this case, we are showing 1 milliampere per major division. So in this particular situation, approximately 4 milliamperes of current are flowing through the circuit. This is well within the safe limits of the body. Now let's change frequencies. Let's go to a higher frequency. Let's go to 10 kilohertz. And again, you can see that the square waveform is taken care of very nicely in this circuit. In fact, the rise time of the square wave is approximately 10 nanoseconds. Very fast rise time. Let's go to a higher waveform frequency. In fact, we are now at 100 kilohertz, and again we have a very clean square wave. Let's go to 250 kilohertz. And again we have a very clean waveform. So it's obvious that the circuit can go up in frequency quite well. Now let's go to a lower frequency. Let's go to 100 hertz. And we find that at 100 hertz the waveform is still a nice clean square waveform. Let's go down another decade. Well, down, not up, okay. Now we are running at a frequency of 10 hertz. And again, the waveform is quite clean. And let's go even lower than that. Let's go down to 1 hertz, or 1 cycle per second. And again, you can see that the waveform is clean. Now you notice at this point there is some slope on the waveform. That is caused by the fact that the output from the driver stage is capacitively coupled to remove the steady DC component that is present in the output of the board. Now we have a 10 kilohertz square wave signal going through the body resistance only. And you will see that if we flip our operation switch here, we can go from a symmetrical waveform to one that is positive going only or negative going only with reference to the ground output of the board, so we can get whatever we want. Now, should we decide that we want to apply RF modulation to that, we flip the other switch, and now we have 3.1 megahertz modulated RF signal coming out of the board, again at a 10 kilohertz rate. And again, we can reference this negative, or we can reference it positive, or we can make it bidirectional. Just depends on what we want it to do. And here we'll turn this off. Now again, this will hold true regardless of the frequency we're operating at. However, the addition of the body capacitance changes things considerably. Now let's see what happens when we add the body capacitance in the circuit. Here we have a 100 hertz square wave being used to modulate the system. Now we're going to add the body capacitance, but before we do that, look at the waveform. It's square wave, and it's approximately 4 milliamperes in current amplitude flowing through the body resistance. Adding the capacitor to the system causes an immediate, rapid leading edge spike of nearly 9 milliamperes. The reason for this is that as the waveform rises, it is charging the capacitor in the body capacitance and causing a sudden increase in current. As soon as the capacitor is charged, the waveform will flatten out. Then as the voltage reverses, the capacitor discharges and charges again in the opposite direction. This means that the circuit, which is producing an average output current of about 4 milliamperes, has a peak current pulse of about 9 milliamperes. Now, this has important implications if we apply the RF waveform to that. If we apply the RF signal at the same time, now we find we have a steady RF signal of approximately 7.5 to 8 milliamperes flowing through the circuit. So there's more current flowing because of the more rapid transitions. And again, because this is constantly charging and discharging the capacitor, we find we can change the reference the same way that we did before. We can make it positive or stable, bidirectional, or we can make it negative based, whichever we want. So we've got the ability to do that. Okay, what happens if we change frequencies? Let's go to a higher frequency. Let's go to 10 kilohertz. We have pretty much the same thing, except that the body capacitance is now not quite as noticeable as far as the waveform change goes. But again, remember that we were running 4 milliamperes on average before, and now due to that body capacitance has pushed the current up to around 7 milliamperes peak. If we go to a lower frequency, let's go to a very low frequency, 10 hertz, and take a look at it. And we find that we still have that rapid spike on the beginning of the pulse, but it's flat through the rest of the pulse. So this is what you see when you drive a parallel resistance and capacitance circuit through a resistance. Now this is being driven through a current limit resistor, which allows a maximum of about 5 milliamperes during the average part of the pulse to occur. But you will have the spike at the beginning and the end of the pulse. Now let's go up in frequency a little bit for stability here. Let's raise it to 100 hertz. Okay, now we can see that nice big pulse. Some circuits will put a capacitor, small capacitor or a large one, in parallel with the current limiting resistor in an attempt to get more current in that leading edge pulse. Well, let's do that. Let's put a 0.022 microfarad capacitor directly across the current limiting resistor in the circuit, and when we do that, this is what we get. We find that we still have, on average, we still have the 4 milliamperes flow, but look at the spikes, the peak voltage. We have to keep dropping this down, dropping this down, dropping this down. And what do we find? We find that now we have peak current spikes going through the body circuit of 270 milliamperes. That's a huge pulse. That's up into the pain threshold region. But because it's such a brief pulse, all you will feel is a spike in your finger, but it's going to definitely be uncomfortable. Now, if you stretch this pulse out, you'll find that it takes longer for the capacitor to charge and discharge because it has a fairly large value. But the leading edge of the pulse, the rise time, is still around 10 nanoseconds. So adding an additional capacitor across the current limiting resistor does not improve the beginning or the rise time of the pulse, but what it does do is increase greatly the amount of peak current that's flowing through the system. It's going to also result in a considerable amount of discomfort for the person using the system. Therefore, I'd recommend not doing that. As one final demonstration, we'll run a waveform sweeping from 10 hertz to 20 kilohertz, first without modulation, RF modulation, then with the RF modulation. Here we're running a peak current of about 7 milliamperes through the body circuit, well within tolerable limits, but easily adjusted by using a 10 kilo ohm resistor. And that's what happens when I put my fingers across part of the circuit. We don't want to do that. So that's basically what we have here. I think we have a workable circuit. I'll finishing up the circuit board layout and the schematic diagram and the parts list, and I'll have more information for you later.